A silent revolution is unfolding in the depths of space. NASA is quietly constructing fleets of robotic cargo modules designed to work together like a swarm, a move that will fundamentally reshape how we explore the cosmos. One of their lead engineers recently stated that the future of deep space exploration is not about single, monumental ships, but about adaptable, collective systems. By the end of this, you will understand the real and surprising reasons this technology is a game changer for human destiny among the stars. We will uncover why this approach is being developed so discreetly and how it could solve the most dangerous problem facing Mars missions. What does it truly take for humanity to become an interplanetary species? Nature has been running the most successful logistics operations for millions of years. An ant colony does not need a foreman ant shouting orders for the entire system to function. Instead, each ant follows a simple set of rules, reacting to its immediate environment and the actions of its neighbors. The result is a resilient, decentralized network that can build complex structures, find food, and defend its home with stunning efficiency. This is the core principle of swarm intelligence, and it is the very blueprint NASA is now using for its cargo modules. The agency did not create this idea from nothing. They are standing on the shoulders of decades of research in fields like distributed computing and artificial intelligence, where scientists studied how simple, independent agents could produce sophisticated group behavior. A leading expert in biomimicry put it perfectly, stating that nature has already solved the problem of collective efficiency, and we are merely learning to apply those principles to our machines. This journey from academic theory to aerospace reality is a story of rethinking intelligence itself. It is not about building one super smart robot, but about creating many simple robots that are smart together. A single module in NASA's planned swarm is not a genius. It is designed to perform a handful of fundamental tasks like navigating, docking, and managing its power. But when you network dozens or hundreds of these modules together, something remarkable emerges. They begin to behave like a single, cohesive organism. If one module fails, the swarm automatically reroutes tasks to its neighbors. If a new module joins, the swarm seamlessly integrates it. There is no central brain to be targeted or to malfunction. This collective resilience, borrowed directly from the insect world, is what makes the concept so revolutionary for the unforgiving environment of space. Understanding this foundational shift from a command and control model to a distributed, collective one is essential. It is the key that unlocks why swarming cargo is not just an upgrade, but a complete transformation of how we will operate beyond Earth. This single point of failure is the nightmare scenario for every mission planner. Picture a lone spacecraft carrying all the oxygen, food, or spare parts for a crew on Mars. A micrometeoroid strike, a propulsion failure, a simple software glitch, and that single thread connecting life to survival is severed. The consequences are unthinkable. Modular cargo swarms are engineered specifically to cut that single thread. They replace it with a robust, interwoven net. The core principle is devastatingly simple, yet profoundly effective. By distributing a mission's essential cargo across dozens, even hundreds of smaller, identical modules, you fundamentally eliminate the possibility of a single catastrophic loss. Think of it not as sending one massive truck, but as dispatching an entire convoy. If one truck breaks down, the others simply drive around it and deliver their portions of the load. The mission continues, A risk management specialist at the Jet Propulsion Laboratory put it bluntly, stating that in the unforgiving environment of space, redundancy is not a luxury. It is a mathematical necessity for survival. This is the cold, hard calculus of deep space travel. Random mishaps are not a matter of if, but when. A swarm architecture accepts this reality and builds resilience directly into its DNA. The loss of one module, or 5 or 10, becomes a manageable logistical problem, not a mission-ending catastrophe. The remaining units automatically recalculate their trajectories, reconfigure their formation, and ensure that a critical percentage of the supplies still reaches its destination. This built-in resilience is revolutionizing mission assurance. It transforms the immense financial and human investments in deep space exploration from a high-stakes gamble into a calculated, manageable risk. The swarm does not promise perfection. It promises persistence, and in the void between worlds, persistence is the only thing that counts. But resilience is only half of the story. The second strategic imperative driving this quiet revolution is an unprecedented level of scalability and flexibility. Think about a future lunar base, beginning as a simple outpost for a handful of astronauts. Over time, its needs explode. It might need to support a permanent crew of 50, host manufacturing facilities, and even serve as a construction dock for a massive ship headed to Mars. A traditional, single-purpose cargo hauler designed for that initial small base would be utterly obsolete for these new, grander phases. It is a bespoke solution for a problem that no longer exists. Modular cargo swarms shatter this old paradigm. They are inherently scalable by design. You are not locked into one giant delivery. You could launch 5 modules in the first year to deliver essential habitats and life support. The following year, you could launch another 50, carrying specialized equipment for fuel production and large-scale construction. All of these units, regardless of when they were built or launched, are designed from the ground up to work together as a single, cohesive system. A systems architect working on the project described it perfectly. He said it is like building with digital Lego bricks in the vacuum of space. You only send up exactly what you need, precisely when you need it. This flexibility allows NASA to respond dynamically to the unpredictable demands of exploration. A mission plan is no longer a rigid, unchangeable document set in stone years before launch. It becomes a living strategy. If scientists on the moon discover a new resource that requires different mining equipment, the next swarm launch can be reconfigured to carry those specific tools. If the decision is made to construct a giant interplanetary vehicle in orbit, the same cargo modules that once supplied a base can be repurposed as the workhorses ferrying components from the moon's surface. There is no need to design an entirely new spacecraft from scratch for every new objective. The swarm is the multipurpose tool, the adaptable backbone for an entire off-world economy. This transforms deep space logistics from a series of monumental, one-off projects into a continuous, flowing, and infinitely adaptable process. The magic that binds this swarm together is a form of artificial intelligence that operates with startling independence. In the void between Earth and Mars, a radio signal can take over 20 minutes to travel just one way. A command to swerve left sent from Houston would arrive to find a module that had already collided with debris 20 minutes earlier. This fundamental law of physics makes constant remote control an impossibility. The swarm must think for itself. Each individual cargo module is far more than a simple container. It is a smart drone, a self-contained world of sensors, processors, and algorithms. Its electronic eyes, a combination of LiDAR and optical cameras, create a real-time, three-dimensional map of its immediate surroundings. It constantly tracks the position, speed, and trajectory of every other module in its vicinity. The onboard software, a marvel of machine vision and predictive modeling, processes this torrent of data to make split-second decisions. It can execute a complex docking maneuver with another module, adjust its formation to avoid a cloud of micrometeoroids, or reroute its entire flight path, all without a single instruction from Earth. A leading researcher in the field put it perfectly, stating that the software is the true marvel here. It is what transforms a collection of parts into a cohesive, intelligent whole. This coordination is managed by something akin to a distributed ledger, a constantly updated and shared record of the swarm's collective state and goals. There is no single point of command. Instead, every module holds a copy of the mission plan and communicates its own status to its neighbors. Through a constant, silent conversation of data packets, the entire swarm reaches a consensus on the best course of action. If one module's sensors detect a hazard, it does not ask for permission to move. It simply moves, and its new trajectory is instantly broadcast, allowing the entire formation to ripple and adjust in response. This is not a fleet being steered. It is a fluid, thinking entity navigating the chaos of space on its own terms. The true breakthrough is not just in building the hardware, but in encoding this resilient, collective intelligence into every line of code. This relentless pursuit of resilience and flexibility leads to an even more powerful force driving the quiet swarm revolution: economics. For decades, the traditional model of spaceflight has been a story of custom-built, monumental endeavors. Each new mission required designing and constructing a unique, colossal spacecraft from the ground up, an incredibly expensive and time-consuming process. It was the equivalent of building a brand new, one-of-a-kind ocean liner for every single transatlantic crossing. Modular cargo swarms completely shatter this unsustainable paradigm. The fundamental shift is standardization. Instead of crafting one perfect, bespoke vessel, NASA is focusing on creating a single, highly capable module design and then building hundreds of them. This approach unlocks economies of scale, a principle that revolutionized manufacturing here on Earth. Think of how the automotive industry produces millions of identical engines or chassis, driving the cost of each individual part down to a fraction of what it would be if crafted alone. A prominent space economist recently emphasized this, stating that standardization is the master key to affordability in space. When you build 100 of the same thing, the cost per unit plummets. This is the simple, transformative math behind the swarm. The immense research and development costs are spread across an entire fleet, not borne by a single spacecraft. The manufacturing process becomes streamlined and automated. Every bolt, every solar panel, every flight computer becomes a known quantity, ordered in bulk and assembled with practiced efficiency. The financial implications of this shift are staggering. It moves ambitious projects like a permanent lunar city or a Mars colony from the realm of fantastically expensive one-off national projects into the domain of financially viable, sustained operations. The model changes from a massive, unpredictable capital expenditure to a predictable, repeatable operational cost. You are not funding the Apollo program all over again. You are funding a supply chain. This is how you build an off-world economy, not with a few spectacular leaps, but with thousands of small, affordable, and identical steps. The swarm is not just a new way to fly, it is a new way to pay for the future. The silence of space is punctuated by a sudden, automated alarm. A cargo module gliding smoothly toward its destination registers a flicker of data. Its sensors paint a terrifying picture, a fragment of orbital debris too small to have been tracked from Earth, now on a direct collision course. In that moment, a command from mission control is not just slow. It is useless. A signal traveling at the speed of light would take long, agonizing minutes to arrive. By the time it did, the decision would already be made, one way or another, by the module itself. This is the brutal reality of communication latency, a fundamental law of physics that no amount of engineering can repeal. The vast distances of space impose an unavoidable time lag on every conversation, turning real-time human guidance into a dangerous fantasy. Modular swarms are built from the ground up to thrive in this disconnected environment. They do not ask for permission. They are designed to act. An engineer on the project captured the philosophy perfectly, stating that they have to teach these machines to think for themselves because they simply cannot be there to hold their hand. This is the essence of localized intelligence. It is a distributed brain where every module is both a sense organ and a decision-making node. They are in constant, chattering communication with each other, sharing a live feed of their sensor data, their fuel levels, and their trajectories. When one module detects that piece of debris, it does not just save itself, it instantly broadcasts a warning. The entire swarm receives this data, and in a fraction of a second, their collective algorithms process the threat. They calculate new, safe paths, adjusting their formation like a flock of birds evading a predator. There is no debate, no central command post deliberating. It is a synchronized, emergent response to a shared environment. This local hive mind allows them to manage far more than just navigation. They can collectively ration power if a solar array fails on one unit, redistributing energy from modules in sunlight to those in shadow. They can decide to abort a complex docking procedure if their shared sensors detect a misalignment, preventing a catastrophic hardware failure. They are making these critical choices entirely on their own, millions of miles from the nearest human. This level of autonomy transforms the swarm from a mere convoy into a living, breathing entity, capable of surviving and adapting to the unpredictable chaos of the cosmos. It is the only way to build a logistics network that does not simply break when the Earth falls silent. This self-sufficiency transforms the swarm from a simple delivery service into an industrial ecosystem. The ultimate goal is to break our total reliance on Earth, and the key lies in what space scientists call in space resource utilization. This is the art of living off the cosmic land, and modular swarms are the perfect tools for the job. Think of a single cargo module, but instead of carrying pre-packed supplies from Earth, it is outfitted with a drill and a small refinery. It lands on a dark, icy patch at the Moon's south pole, extracts water from the soil, and then uses solar power to split that water into its basic components, hydrogen and oxygen, the very same propellants that power our most advanced rockets. Another module, designed as a mobile fuel depot, docks with it, receives a fresh load of rocket fuel, and then flies off to rendezvous with a spacecraft heading to Mars. The ship refuels and continues its journey, all without a single drop of fuel having been launched from Earth. This is the game-changing loop. An in-space resource pioneer famously predicted that the first trillionaire will be the one who masters asteroid mining, and swarms are the workforce that will make it happen. The brilliance of the modular approach is its sheer adaptability. The same basic platform can be reconfigured on the fly. One mission, a module, is a miner. The next, it is a mobile processor. The next, it is a tanker. There is no need for a dozen different, specialized spacecraft. You have a fleet of universal workers that you can assign to different tasks as needed. This creates a scalable, in-space supply chain, the absolute cornerstone of a true spacefaring civilization. It means that the infrastructure for building a city on Mars or a station in deep space can be manufactured from materials already out there, using power from the sun. The swarm becomes the circulatory system for this new off-world economy, moving raw materials to processors, finished goods to construction sites, and fuel to waiting ships. This is how we stop being visitors in space and start becoming permanent residents. That very independence from Earth is also the source of its quiet development. The question is not just why NASA is building this, but why it is doing so without the usual fanfare. The answer lies beyond engineering and economics, in the sober realm of global strategy. Possessing a robust and scalable space logistics system is a tremendous strategic advantage, comparable to a nation controlling the world's most vital sea lanes centuries ago. A geopolitical analyst specializing in space policy put it bluntly, stating that whoever commands the supply lines to the Moon and Mars commands the high ground of the entire next century. This is the unspoken dimension. By building this modular infrastructure discreetly, NASA is ensuring national preeminence in space. They are constructing a backbone so flexible and resilient that it can support purely scientific missions, a burgeoning commercial economy, and, if ever necessary, secure strategic objectives, all without requiring a public declaration of intent. It is about preventing a space-based logistics gap from ever emerging against competing nations. Think of it not as a weapon, but as the ultimate enabling technology. The nation that owns the most reliable delivery network for water, fuel, and building materials in cislunar space effectively sets the rules for the new off-world economy. They become the indispensable partner, the port authority for the solar system. This quiet effort is a long-term insurance policy, a way to secure a position of leadership through undeniable capability rather than through proclamation. It is a race not for a single flag-planting moment, but for the fundamental infrastructure that will underpin all future activity beyond our atmosphere. The real power does not always roar. Sometimes it simply arrives in a silent, coordinated swarm, ready to build the future. At the heart of this silent coordination lies an architectural blueprint so fundamental it could be considered a constitution for the swarm. For these modules to act as a single, fluid entity, they must share a universal language and a universal handshake. This is the world of standardized interfaces and protocols, the invisible glue that binds individual drones into a collective intelligence. The core challenge is interoperability, ensuring that a module built by NASA in 2025 can physically dock and digitally converse with a module built by a European consortium in 2030 or a private company in 2035. Without this universal compatibility, the grand vision of a scalable, resilient swarm collapses into what one lead designer bluntly called a pile of junk floating in formation. The solution is a set of rigorously defined standards, essentially a USB port for space. The physical docking mechanism is a masterpiece of mechanical simplicity and robust engineering. It is not a complex, custom-built clamp, but a symmetrical, androgynous port. This means any module can dock with any other module from any direction, with no right side up or wrong side down. The port uses a combination of strong, passive magnets for initial capture and alignment, followed by a series of mechanical latches that create a rigid, airtight seal. This design allows for a degree of error, forgiving minor misalignments during the automated docking process. The true magic, however, happens after the click. Once physically connected, the modules engage in a digital handshake. A standardized communication protocol instantly initiates, a pre-agreed digital language that allows the two units to introduce themselves. They exchange vital statistics, their unique identification, remaining fuel levels, power status, and the cargo they carry. This shared protocol is what enables the swarm's distributed intelligence. A module in distress can broadcast a standardized help signal, and every other module, regardless of its manufacturer, understands the message and can compute a collective response. This open architecture is arguably more revolutionary than the modules themselves. It creates a collaborative ecosystem, inviting international partners and commercial entities to build compatible components, dramatically accelerating the pace of space development. The standard becomes the great enabler, turning a proprietary NASA project into the foundational infrastructure for an entire off-world civilization. The Lunar Gateway offers a perfect glimpse into this future in action. Think of it not as a solitary space station, but as the first interplanetary seaport. Orbiting the Moon, it will serve as the central hub where the cargo swarm concept becomes a daily reality. Its entire architecture is being designed from the ground up to be swarm native. A Gateway program manager put it clearly, stating the station is built to manage and utilize these distributed systems. This means its docking ports, its communication systems, and its power grid are all optimized to interact not with one occasional visiting ship, but with a constant flowing traffic of robotic modules. Picture the scene around the gateway. It is not a quiet, lonely outpost. It is a hive of automated activity. A swarm module arrives from Earth carrying a fresh shipment of scientific experiments. It does not wait for a human to guide it in. Using its own sensors and the universal docking standard, it autonomously maneuvers into an available port, locking itself into place with a silent, magnetic click. Within hours, its cargo is transferred by internal robots, and the now empty module is released, either to begin its return journey to Earth or to be reassigned a new task. Another swarm, having finished mining water ice from the lunar South Pole, arrives to offload its precious cargo of refined propellant into the Gateway's storage tanks. This fuel will then be used to top up the landers that carry astronauts down to the lunar surface, creating a closed-loop supply chain. The Gateway becomes the orchestrator, the logistical brain that coordinates this ballet of robotic workers. It is the proof of concept, the busy port that demonstrates how this entire system will scale for the much longer, more complex journey to Mars. By perfecting the swarm around the Moon, we are building the template for the entire solar system. This strategic shift toward a universal standard opens the door for a revolution not just in technology, but in economics. NASA has no intention of building every single one of these cargo modules itself. The real power of the swarm lies in its ability to catalyze an entire industry. The agency's quiet development of the core technology and its insistence on open standards is a deliberate move to foster a commercial market for space logistics. They are creating the playing field and the rules, then inviting private industry to bring the players and the innovation. A venture capitalist deeply immersed in space tech put it perfectly, explaining that NASA is building the railroad and they are inviting everyone to run their own trains on it. This is the public-private partnership model in its most ambitious form. Companies like SpaceX, with its vast experience in reusable rockets, Rocket Lab with its focus on specialized small satellites, and a host of new startups are now being actively encouraged to develop their own cargo modules that are fully compatible with the swarm's universal docking and communication protocols. This creates a vibrant, competitive ecosystem. Instead of a single government-led design, you get a flowering of different approaches. One company might specialize in modules with extra shielding for volatile chemical cargoes. Another might perfect a design with vast, ultra-efficient solar arrays for long-duration missions. A third might focus on creating the most cost-effective, bare-bones transport unit for bulk materials like water or regolith. This competition drives down costs and accelerates the pace of innovation at a speed a single government agency could never match on its own. the burden on the taxpayer is dramatically reduced as NASA transitions from being the sole builder to being an anchor tenant, a guaranteed customer for these commercial delivery services. They can issue a contract for the delivery of 10 tons of cargo to the Lunar Gateway and simply choose the most reliable and affordable bid from a range of private providers, all using compatible swarming technology. This model transforms space from a government-owned frontier into an open economic domain where innovation and efficiency become the primary currencies. This logistical network holds within its design a solution to one of our most pressing orbital crises. The very same architecture designed to deliver our future among the stars could be tasked with cleaning up the dangerous legacy of our past. A dense and growing cloud of space debris now encircles our planet, a chaotic field of defunct satellites, spent rocket stages and countless fragments, all traveling at speeds faster than a bullet. Every single piece is a potential mission killer. The threat is so severe that a leading space sustainability advocate made a stark observation, stating that the same technology that delivers our future could also be tasked with cleaning up our past mistakes. This is not a secondary thought, but a core capability being engineered into the swarm's flexible design. Imagine a standard cargo module, but instead of a pressurized container for supplies, its payload bay is filled with a different kind of tool. It could deploy a large, lightweight net, casting it around a tumbling, derelict satellite to capture it. Another might use a precise harpoon system, skewering a larger piece of debris and attaching a small to-orbit thruster. More advanced concepts even involve using targeted lasers to gently nudge smaller fragments, altering their trajectory just enough to send them burning up harmlessly in the upper atmosphere. The swarm's inherent advantages make it uniquely suited for this dirty work. No single module needs to be a dedicated debris removal vessel, an expensive and specialized platform. Instead, a handful of modules within a larger logistics fleet can be temporarily reconfigured for a clean-up operation. Their distributed intelligence allows them to work together on a complex capture, coordinating their approach angles and sharing sensor data to safely grapple with a spinning, unpredictable object. Their resilience means that if one module gets hit by a tiny, untrackable fragment during the operation, the mission does not fail. The others simply adapt and complete the task. This transforms the swarm from a simple supply chain into a custodial force, a self-cleaning system for the vital orbital pathways around Earth. By actively managing this debris field, we are not just protecting our own missions. We are preserving the orbits around our planet as a usable, sustainable resource for all of humanity, turning a looming threat into a manageable maintenance task. This shift in engineering mirrors a deeper change in our collective imagination. For generations, the icon of space travel was the singular, heroic vessel, a gleaming monolith like the Apollo Command Module or the Space Shuttle. These were cathedrals in the void, magnificent and self-contained, carrying the hopes of a planet on a fragile, solitary journey. The modular swarm shatters that archetype. It replaces the cathedral with an entire city, a bustling, interconnected ecosystem where no single piece is irreplaceable. A prominent science historian observed that we are moving from the age of the cathedral to the age of the city in space. This is not merely a change in design, it is a fundamental rethinking of our relationship with technology beyond Earth. The old model celebrated individual grandeur and heroic against all odds survival. The new model prioritizes collective function, resilience, and quiet, persistent adaptation. It values the health of the entire network over the fate of any single component. This philosophical transition is absolutely necessary for the dream of becoming a multi-planetary species. A cathedral can be a monument, but only a city can be a home. You cannot build a lasting civilization on the back of a few perfect machines. You build it on the foundation of a robust, self-healing system, one that can lose a dozen parts and still continue to grow. This is the psychological leap from placing our faith in a single, perfect spearhead to trusting in the strength of an unbreakable net. It means accepting that the future in space will be less about the drama of a lone ship and more about the quiet, relentless efficiency of 1,000 interconnected workers. Our technology is becoming less like a knight in shining armor and more like a living, breathing forest, capable of weathering any storm because its roots are woven together. Every line of code and every autonomous decision made by these swarms is first forged in the fires of simulation. Long before a module feels the cold vacuum of space, it lives 1,000 digital lives inside supercomputers. Engineers construct painstakingly detailed virtual universes, modeling not just the predictable pull of gravity, but the chaotic spray of micrometeoroids and the subtle drift of solar radiation pressure. Here, in a world made of pure math, they unleash their digital swarms and then proceed to break them. They introduce catastrophic failures, sever communication links between modules, and throw virtual debris onto collision courses, all to probe the limits of the swarm's collective intelligence. A simulation lead for the program put it starkly, stating that they fail 1,000 times in simulation, so they only have to succeed once in space. This brutal digital proving ground is where the swarm's resilience is truly born, where its algorithms learn to cope with the unpredictable. But the testing does not stop in the virtual world. The concepts then move to Earth-based analogs, harsh environments that stand in for distant planets. In the stark deserts of the American Southwest, you might see a team of engineers guiding a fleet of miniature rovers. These terrestrial surrogates are not operating in a clean lab. They are navigating rocky, unpredictable terrain, their sensors blinded by dust storms and their communications deliberately disrupted, forcing them to rely on the same localized, peer-to-peer networking their orbital cousins will use. This two-step process is non-negotiable. The high-fidelity simulations test the pure logic of the swarm against the immutable laws of physics, while the field tests challenge that logic with the messy, imperfect reality of a natural environment. It is here, in these controlled crucibles of failure, that the silent, coordinated dance of the swarm is choreographed and perfected, long before the first rocket ever ignites. This decentralized architecture, for all its resilience, opens a new digital frontier fraught with peril. The very network that gives the swarm its intelligence also presents a vast and tempting attack surface for any malicious actor. In the cold logic of cyber warfare, a single compromised module is no longer just a piece of broken hardware. It becomes a rogue agent, a weapon hiding in plain sight within the formation. A cybersecurity expert for space systems delivers a chillingly simple warning, stating that a single compromised node could potentially compromise the entire swarm's mission. Imagine the nightmare scenario. A module, its security protocols breached through a sophisticated digital attack, receives a malicious command. Its thrusters fire at full power, not to avoid debris, but to deliberately ram into a multi-billion-dollar space station or another critical swarm. The distributed intelligence that allows the swarm to adapt becomes its greatest vulnerability, as the rogue module's false data and malicious actions ripple through the network, potentially confusing the entire collective. Securing this distributed mind is a challenge unlike any other. You cannot simply build a firewall around a single central server because no such server exists. The defense must be as decentralized as the system itself. This has led to the development of revolutionary encryption methods, often described as blockchain-inspired. Every piece of data shared between modules, every trajectory update and status report, is wrapped in layers of unbreakable cryptographic code. More importantly, the swarm is being taught a form of digital herd immunity. Each module constantly monitors the behavior of its neighbors, looking for statistical anomalies that betray a compromise. Is one module transmitting impossible sensor readings? Is it consuming power in an erratic pattern? Is its proposed trajectory a dangerous deviation from the swarm's shared goal? When such red flags are raised, the healthy modules do not wait for a command from Earth. They can collectively vote to isolate the suspect unit, severing its digital communication links and effectively casting it out of the collective mind. The compromised module becomes a silent, inert piece of space junk, its threat neutralized by the immune response of the swarm it once belonged to. This constant, silent vigil is the price of autonomy. The swarm must not only be smart enough to navigate the cosmos, it must be wise enough to protect itself from the enemies it cannot see. The humble cargo module is merely the larval stage of a far more ambitious creature. Its true purpose goes far beyond simple delivery, evolving into the foundational worker for the first automated construction crews in space. Think of the initial cargo missions as a training program, a way for the swarm to master the fundamentals of coordinated flight and docking. Once that dance is perfected, the real transformation begins. The same standardized chassis that once carried water and food can be refitted with entirely new payloads. Some modules become flying quarries, their holds filled with metallic asteroids or processed lunar regolith. Others are equipped with powerful, zero-gravity 3D printers, capable of extruding molten metal or composite materials into precise, predetermined shapes. A third type might transform into a mobile factory, armed with dexterous robotic arms and advanced welding tools. A visionary roboticist on the project captured this progression perfectly, stating that the cargo swarm is the Trojan horse for the construction swarm. We learn to deliver, then we learn to build. This is the logical and thrilling extension of the entire concept. Instead of launching a gigantic, fragile space telescope like the James Webb in one incredibly risky piece, we would launch the raw materials and the robotic factory in a swarm of manageable modules. In the safe, stable environment of a lunar orbit, the swarm would then assemble the telescope, piece by precision-crafted piece, creating a structure that would be far too large and complex to ever launch from Earth. The same process could build vast solar power stations, radiation-shielded habitats for Mars, or even the skeletal frames of generation ships. The key technological leap is not in the hardware, but in the software, advancing from simple collision avoidance to complex collective task management. The swarm would need a shared digital blueprint, a kind of distributed consciousness of the final design. One module, the master printer, would begin fabricating a primary truss. Another, acting as a mobile crane, would maneuver the finished piece into place. A third would arrive to perform the microscopic welding, all while a network of sensor modules scans the work for imperfections in real time. There is no foreman, only a symphony of specialized agents, each performing its simple part in a grand, coordinated ballet of creation. This is the ultimate promise of the swarm, to become the hands and tools that build our future in the cosmos, not with a single loud launch, but with the quiet, persistent hum of 10,000 robotic workers. But this digital consciousness raises a profound and unsettling question. If a collective machine intelligence makes a critical decision that leads to a catastrophic failure, who do we hold accountable? Is it the programmer who wrote the original algorithm, the mission operator who authorized its launch, or the artificial intelligence itself that interpreted the data in a way no human could have predicted? The lines of responsibility blur into a legal and ethical gray area. A leading ethicist in the field frames the dilemma perfectly, asking at what point a collective machine intelligence requires a new legal and ethical framework. We are entering uncharted territory where our traditional concepts of fault and liability are completely inadequate. A single module has no malicious intent, but a swarm can exhibit emergent behaviors that were never explicitly coded, creating outcomes that are impossible to attribute to a single human actor. This forces a fundamental shift from asking who is to blame to asking how we design systems that are inherently accountable. The solution likely lies in a concept known as explainable artificial intelligence. This means engineering the swarm's decision-making process to be transparent and auditable. Every maneuver, every choice to reroute or dock, must leave a detailed digital trail that human overseers can later reconstruct and understand. It is not enough for the swarm to be smart. It must also be able to justify its actions in a language we can comprehend. This technological transparency is the first, crucial step toward building trust in these autonomous systems, but it is only the beginning. The real challenge extends far beyond code into the realm of global politics and human cooperation. The potential for conflict is inherent. One nation's defensive swarm maneuver could be perceived by another as an aggressive act, sparking a diplomatic crisis or worse. Without clear, internationally agreed upon rules of the road for space, this powerful technology could become a source of tension rather than a tool for unity. This urgent need has sparked conversations about the creation of new regulatory bodies, akin to an air traffic control system for cis-lunar space. These organizations would not micromanage every swarm, but would establish vital protocols for communication, right-of-way, and coordinated emergency responses. They would serve as neutral arbiters, ensuring that the shared highways of space remain safe and accessible for all. The ultimate goal is to weave a fabric of international treaties that ensure these autonomous systems are used strictly for peaceful and cooperative purposes, benefiting all of humanity. The silent swarm is not just a test of our engineering prowess. It is a mirror held up to our own ability to govern ourselves, to collaborate on a global scale, and to wisely steward the powerful tools we create. The future of space may well depend less on the intelligence of our machines and more on the wisdom of our laws. The democratic process of a honeybee swarm offers a stunning parallel to the challenges these robotic fleets must solve. Thousands of bees must collectively choose a single new home from several potential sites, a life or death decision with no single bee in command. They achieve this not through a simple vote, but through a nuanced dance of recruitment and feedback. Scout bees return from their explorations and perform a waggle dance, its intensity and duration communicating the quality of the site they found. More enthusiastic dances for superior locations attract more scouts to go and investigate for themselves. This creates a positive feedback loop. As more scouts converge on the best site, their collective buzzing at that location grows louder, creating an audible quorum signal that finally triggers the entire swarm to lift off and move as one. A biologist studying this collective behavior clarifies that the bees do not vote. They reach a consensus through a sophisticated process of information sharing and feedback. This natural algorithm is remarkably robust against bad information or stubborn individuals because it is the weight of the collective's confirmation that ultimately decides. Engineers are now encoding these very same biological principles, quorum sensing and positive feedback loops, directly into the swarm's digital DNA. Instead of a waggle dance, a cargo module that finds a clear, fuel-efficient trajectory will broadcast a high-priority data packet, a digital signal of confidence that recruits other modules to follow its path. The swarm does not take a head count, it senses when a critical mass of its members has converged on the optimal solution, at which point the entire collective seamlessly commits. This bio-inspired logic makes the artificial swarm smarter and more resilient, allowing it to filter out noisy sensor data or a single module's erroneous calculation by trusting the emerging pattern of the group. The universe has been running the most advanced distributed computing networks for millions of years, and we are only just beginning to learn its language. Every gram saved in orbit translates to a cascade of fuel savings and expanded mission capabilities. This brutal efficiency requirement has ignited a parallel revolution in the laboratories where these modules are born, a quiet transformation in the very substances from which they are forged. The swarm paradigm demands a new kind of spacecraft skin, one that is simultaneously a featherweight and a fortress. A materials scientist deep in this work captures the essence of the challenge, stating they are not just building spacecraft, they are pushing the entire field of materials engineering forward. The traditional aluminum shells of old satellites are simply too heavy and too vulnerable for this new era. In their place, engineers are weaving intricate lattices from carbon nanotubes and advanced composites, creating structures that possess the strength of titanium but the density of balsa wood. These are not solid plates but intricate, three-dimensional meshes, optimized by artificial intelligence to place material only where it is absolutely needed to handle stress, resulting in skeletons that are largely empty space yet can withstand the violent shaking of a rocket launch. But the innovation does not stop at being strong and light. The modules must also be smart. Researchers are perfecting self-healing polymers, plastics embedded with microscopic capsules of liquid resin. When a micrometeoroid, smaller than a grain of sand but traveling at astronomical speeds, punctures the hull, these capsules rupture at the point of impact. The released resin instantly hardens upon contact with the vacuum of space, forming a seamless, airtight seal in a matter of seconds. It is a biomimetic marvel, giving the module a scar, a permanent record of a threat it survived without human intervention. This relentless drive for perfection extends to how these materials are formed. Additive manufacturing, or 3D printing, is fundamental. Instead of machining parts from solid blocks of metal, which can waste over 90% of the material, printers build components layer by atomically precise layer, using only the exact amount of material required. This allows for the creation of impossibly complex internal geometries, cooling channels and wiring conduits printed directly into the walls of a thruster nozzle, something impossible to achieve with any other method. The relentless demands of the swarm are forcing these technologies out of prototype labs and into production, accelerating their maturity and driving down their cost. The ultra-lightweight composites developed for a module's chassis are now finding uses in the next generation of commercial aircraft and high-performance automobiles. The self-healing plastics are being adapted for pipelines and other critical infrastructure on Earth. The swarm is not just a consumer of advanced materials, it is a powerful engine for their creation, spinning off breakthroughs that ripple back to strengthen our own world. The silent, coordinated dance of a robotic swarm faces an ultimate test in the deep cold of permanent shadow. A module cannot rely on collective intelligence if its own individual power reserves run dry, leaving it a frozen, inert tombstone in the void. This is the power problem, a fundamental challenge that pushes energy technology to its absolute limits. For missions operating in the darkness of a lunar crater or during the long Martian night, conventional solar panels are simply useless. The solution requires a source that is both incredibly dense and utterly reliable, drawing engineers back to a technology with a long and storied history in space exploration, the radioisotope thermoelectric generator. An energy systems engineer working on the Swarm project states the reality without hesitation, explaining that for sustained operations in dark environments, nuclear power is not an option, it is the only option. An RTG is a marvel of elegant simplicity. It contains a pellet of a radioactive material, most commonly plutonium-238, which naturally decays over decades, generating immense heat as a byproduct. This heat is then converted directly into electricity through solid-state thermocouples, with no moving parts to wear out or break. It is a quiet, steady heartbeat of power that can last for 50 years or more. But RTGs have a significant drawback. They provide a relatively low amount of electrical power, enough for a single module's basic systems, but perhaps not for high-energy tasks like processing raw materials. This limitation is driving the parallel development of an even more powerful solution, compact fission reactors. These are miniature versions of terrestrial nuclear power plants designed to fit inside a cargo module. Unlike an RTG, which relies on passive decay, a fission reactor sustains a controlled chain reaction, generating vastly more power, enough to run an entire mobile refinery or a high-powered laser communication array. The choice becomes a strategic one. Do you equip your swarm with many modules powered by long-lived, low-output RTGs for persistent presence, or a few modules with high-output fission reactors for intensive industrial work? The answer is likely a hybrid fleet. Some modules will be the marathon runners, powered by RTGs to act as permanent navigation beacons or communication relays in shadowed regions. Others will be the sprinters, powered by compact reactors, deployed temporarily to specific sites to perform a few months of high-intensity work before moving on. This nuclear backbone is what enables the swarm's most profound promise, true long-term autonomy far from the sun's warm embrace. Without this steady, internal fire, the most intelligent swarm in the universe would simply fall silent, its collective mind extinguished by the cold. Yet for all their intelligence, these swarms are not meant to replace human judgment, only to extend its reach. The ultimate vision is a seamless partnership where an astronaut can issue a simple command and watch as 1,000 autonomous workers spring into coordinated action. This demands a revolution not in robotics, but in design centered on the human experience. How do you build an interface for controlling an entire robotic fleet without drowning the user in a flood of data? The answer is being forged in human factors laboratories, where the principle is not to give the astronaut more information, but to give them only the information that matters. A human factors designer on the project crystallized the ambition, stating their goal is to make controlling 1,000 modules feel as simple as directing a single assistant. The key is intuitive, high-level language. An astronaut would not manually pilot a single module to a specific set of coordinates. Instead, they might point toward a section of the lunar surface and say, "Build a landing pad here." The swarm's distributed intelligence would then pass that command, break it down into 1,000,000 subtasks, and assign them automatically. Individual modules would begin surveying the terrain, others would start processing local regolith into building material, and a third group would begin the precise work of fabrication and assembly, all without another direct order. The primary tool for this interaction is an augmented reality visor. Through this transparent display, the astronaut sees the real world, but overlaid with a shimmering digital schematic of the swarm's collective mind. Each module is represented by a simple, glowing icon. Its color indicates its status: green for optimal, yellow for low power, red for a fault. To interact, the astronaut simply looks at a module, or a group of them, and uses a glove-mounted controller or even voice commands to assign a new objective. The swarm's complex internal state is translated into a visual language a human can understand at a glance. This human-centered design is what prevents the system from becoming overwhelming. The interface is built on a concept called progressive disclosure. By default, the astronaut sees only a calm, high-level overview. Are the swarms healthy? Are they on schedule? Only if they choose to drill down into the data do they see the intricate dance of individual trajectories and power levels. It is the difference between asking a factory manager about the health of the production line and asking them to diagnose a single faulty bolt on a specific machine. The system is designed to handle the bolts, freeing the human to focus on the big picture, the strategy, the creative decisions that machines cannot make. This elegant fusion of human intuition and machine precision is the final, critical link in the chain, transforming the swarm from a marvel of engineering into a true extension of human will in the cosmos. The roadmap from laboratory concept to interplanetary workhorse is already being charted with clear, deliberate milestones. We will not see a 1,000-strong fleet overnight. The strategy is one of incremental proof, a careful dance of testing and validation that builds confidence with every successful mission. A program strategist outlines their philosophy clearly, stating that their roadmap is incremental. They prove the technology in Earth orbit, validate it at the Moon, and then deploy it for Mars. The first tangible demonstrations are scheduled for the very near future. Within the next few years, look for a small cluster of prototype modules, perhaps just 3 or 4, to be launched into low Earth orbit. Their mission will be deceptively simple. They must demonstrate the core swarm behaviors autonomously, flying in a tight formation, handing off a simulated cargo container between them, and executing a collective avoidance maneuver when presented with a virtual debris field. This is the kindergarten class for swarm intelligence, learning the absolute fundamentals of cooperation in the relative safety of Earth's backyard. Success here proves the underlying software and hardware can function as a cohesive unit. The next major leap comes with the Artemis program in the early 2030s. Here, the swarm graduates from a classroom exercise to a real-world supporting role. Small fleets of dedicated modules will be tasked with the gritty work of lunar logistics, autonomously ferrying cargo between the lunar gateway and various landing sites on the Moon's surface. They will deliver spare parts, scientific instruments, and potentially even pre-packaged habitat elements for astronauts. This is the ultimate validation phase, where the swarm must operate reliably for months or years at a time, navigating the complex gravitational environment around the Moon and dealing with the abrasive lunar dust. It is one thing to perform a flawless dance in the clean vacuum of Earth orbit. It is another to do it while supporting a permanent human presence on another world. Passing this test sets the stage for the grand finale, a fully autonomous Mars cargo pre-positioning mission launching in the 2040s. This is where the swarm's true value is realized. Years before the first human footsteps are ever taken on the Red Planet, a fleet of dozens of cargo modules would begin their slow, silent journey. They would carry the essential infrastructure for survival, the habitats, the power plants, the rovers, and the return vehicle fuel, all prepositioned and waiting. Upon arrival, they would not simply crash land. They would use their collective intelligence to perform a synchronized, precision landing within a designated zone, creating a ready-made outpost for the human pioneers who will follow. This stepping stone approach transforms an audacious vision into a manageable, funded, and utterly achievable reality, turning the silent revolution into the backbone of our interplanetary future. The relentless drive to perfect these cosmic cargo fleets is quietly seeding a technological revolution back on our own planet. The same breakthroughs in artificial intelligence that allow a swarm to navigate the void without human intervention are already finding their way into the systems that will guide our cars and drones. Think of a future city where fleets of autonomous delivery vehicles flow through streets with the same silent, fluid coordination as a swarm in orbit, avoiding collisions and optimizing traffic in real time, all powered by algorithms born from the challenge of deep space. A technology transfer officer from the program puts it perfectly, stating that the greatest return on investment in space technology often is not in space. It is in the spin-offs that improve life on Earth. This is the powerful and often overlooked ripple effect. The ultra-lightweight composites, engineered to save every precious gram on the journey to Mars, are now being integrated into the next generation of passenger aircraft. These new airframes are so strong and so light that they slash fuel consumption dramatically, reducing carbon emissions and making air travel more sustainable for everyone. But the applications spread far beyond transportation. Picture a vast agricultural field where a swarm of small drones, equipped with the same distributed intelligence as their spacefaring cousins, flies low over the crops. They are not just taking pictures, they are communicating with each other, identifying a localized pest outbreak or a patch of soil in need of water, and then dispatching a single drone to deliver a precise, tiny dose of pesticide or fertilizer exactly where it is needed. This is precision farming on a grand scale, eliminating waste and boosting yields using technology forged for the cosmos. In the chaotic aftermath of an earthquake or a hurricane, these principles become a lifeline. Search and rescue teams could deploy a swarm of small, rugged robots into a collapsed building. Like a collective digital bloodhound, these machines would fan out, sharing a real-time map of the unstable wreckage. If one robot finds a survivor but its path is blocked, it does not give up. It instantly relays the victim's location to the entire swarm, and the collective intelligence calculates the fastest, safest way for a different robot to reach them, coordinating a rescue in minutes instead of hours. The quest to build a resilient future in space is, in a very real sense, building a smarter, safer, and more efficient world right here at home. The allure of a single, majestic spacecraft is a powerful one, and it fuels the most common criticism of the swarm model. Detractors argue that by replacing one complex machine with hundreds of them, you are not eliminating failure points, you are multiplying them. A respected skeptic of mega projects puts it bluntly, stating that the allure of distributed systems is strong, but the devil is in the distributed details. This seems like a logical concern. If one module has a 1% chance of failure, then 100 modules seem to guarantee a problem. But this criticism fundamentally misunderstands the core architecture of resilience. A traditional mission is a chain, and a single broken link means total failure. A swarm is a net. The failure of one node is not a catastrophe. It is a statistical expectation that the system is designed to absorb. The question is not whether a module will fail, but whether the swarm can continue its mission despite that failure. Simulations run on supercomputers consistently show that even with a 10% random failure rate across a large swarm, over 99% of the cargo still reaches its destination. The devil is not in the details of individual failure, but in the emergent resilience of the collective. Another frequent argument questions the sheer cost of building so many individual units. Would it not be cheaper to just build one big, reliable ship? This perspective ignores the revolutionary economics of standardization. The immense cost of space missions has never been in the raw materials, but in the research, development, and custom fabrication of one-off designs. Building the first swarm module is expensive. Building the 100th is remarkably cheap. thanks to automated assembly lines and bulk purchasing of standardized components. This model transforms a monumental capital expense into a predictable, scalable operational cost, a shift that space economists argue is the only viable path to a sustained presence beyond Earth. Perhaps the most nuanced critique involves the software itself. Can we truly trust a decentralized, autonomous system to make life or death decisions without human oversight? This is a profound ethical challenge, not just a technical one. The response from engineers is not to claim perfection, but to demonstrate superior performance. In millions of hours of simulation, autonomous swarms have consistently outperformed human-guided systems in reacting to sudden, unexpected threats like debris clouds. The system's distributed intelligence acts as a form of collective wisdom, filtering out the errors of a single sensor and arriving at a safe consensus faster than any human operator could even process the initial alert. These criticisms are essential, forcing a harder look at the technology's real-world viability. By confronting them directly with data and logical counter-arguments, we move from blind enthusiasm to a clear-eyed understanding of both the immense promise and the manageable risks of this quiet revolution. The silent construction of modular cargo swarms represents a strategic masterstroke, one that fundamentally redefines the economics and safety of living among the stars. This is not merely a new way to ship supplies, it is a complete philosophical shift from a fragile, monumental approach to a resilient, distributed one. We have traced this journey from its origins in the swarm intelligence of the natural world, through the cold calculus of eliminating single points of failure, to the brilliant software that grants these machines collective thought. The implications ripple outward, promising not just survival, but the rise of a true off-world economy built on in-space resources and automated construction. This distributed model is the indispensable key, the only practical path to a future where humanity is not just visiting space, but is a permanent presence there. In the words of Arthur C. Clarke, the only way of discovering the limits of the possible is to venture a little way past them into the impossible. NASA's quiet work on these cargo swarms is precisely that bold venture, a deliberate step into a future that was once deemed unattainable. We would love to hear your perspective on this future. What aspect of this technology excites you the most? Share your thoughts in the comments and subscribe to stay connected to the story of humanity's next great